Welcome to the fourth session on electrolytic conductance. Here we will be dealing with ionic mobilities, ionic conductance, their relation as well as the measurement of ionic mobilities. When we check the molar conductance at infinite dilutions of different electrolytes, let it be of the same category, that is a univalent itself, for example, HCl and sodium chloride. So, HCl means again that is unipositive ion and chloride ion is a uninegative ion. And when we take sodium chloride or potassium chloride, you can take any univalent electrolyte, let it be potassium nitrate. And I will take sodium nitrate, Na plus N. All these are univalent electrolyte, both cation as well as anion, they are having the valency 1. Okay. Now, when the molar conductance at infinite dilution is reached, both H plus which carries unipositive charge, Cl minus carries uninegative charge. In a similar way, all these cations and anions are carrying unit positive and unit negative charges. So, actually when we think, it should be like this, like infinite dilution, all the values of these should be same, because all the ions are conducting, all cations carry unit positive charges and anions carry unit negative charges. And if you are taking same concentration of the electrolyte, suppose I am taking only 1 mole of an electrolyte. So, all this should have the same value, but in actual practice they are different. For example, when I take HCl and NaCl, you can see the chloride ions in both cases they will be having the same value for molar conductance, while H plus and Cl they are different cations. Even though they are having unit positive charges, their molar conductances differ. Why do they differ? This is because of the factor that H plus ions are fast moving ions. While Na plus ions, they are a bit more larger in size. So, compared to H plus, they move slowly. Since H plus ions are moving faster, what happens is H plus ions will carry more current. Na plus ions do not move that fast and therefore, they cannot carry as much as current as H plus carries. So, we introduce a new term known as ionic mobility, somewhat related to speed of the ion. Ionic mobility mu is defined as the distance travelled in centimeter, or it can be in meters if we consider the SI unit, by an ion in 1 second under a potential gradient of 1 volt per centimeter. In SI it will be, instead of centimeter, it will be meter. So, what is ionic mobility? It is the distance travelled in centimeters by an ion in 1 second. So, distance travelled in centimeters per second under a potential gradient of 1 volt per centimeter. Okay. So, ionic mobility, it is represented by the letter mu, and mu is equal to speed of the ion divided by potential gradient. Speed of the ion means it is, we can say in both ways, either in SI units or CGS unit. In CGS unit, it is centimeter square per volt per second inverse, and in SI units it is meter square plus volt raised to -1 and second inverse. But when we think of the ionic mobilities, do not confuse it with they are moving with an excellent speed, they do not travel with a very high speed as a gaseous molecule, they are very small when compared to the velocity of the gas molecules. So, this determines, that is the ionic mobility gives us an idea about how much current an ion can carry when applied in an electric field. Now, how will you measure this ionic mobility? Only then we can get an idea like which ions move faster and therefore they carry more current. So, you can compare which electrolyte will be conducting more and which will be conducting less. For that, we use an experiment to determine the ionic mobility of the ions. So, this is an apparatus used for determination of ionic mobility of an ion. Here, we have a tube, a glass tube, which is of uniform diameter throughout. It should be of same diameter, it should not vary, okay, same diameter, which contains electrolytes, and that too you should take two electrolyte. One is known as the principal electrolyte, Why is it called principal electrolyte? This is the electrolyte from which we are going to measure the ionic mobility. And you can have a secondary electrolyte, or it is also known as indicator electrolyte. Okay, so we should have two electrolytes. One is a principal electrolyte, the other one is an indicator electrolyte. Now, there are conditions for these two. Whatever be the principal electrolyte, the indicator electrolyte should have the anion in common. With the principal electrolyte. Okay. So, the anion of the principal electrolyte or the electrolyte from which we have to determine the ionic mobility should have the same anion for the indicator electrolyte. For example, in this case, in this experiment, we are going to determine the ionic mobility of K plus ion, that is a potassium ion. So, I will be taking a principal electrolyte which contains a potassium ion. For example, in this experiment, it is KCl. And the concentration taken is 0.1 normal or molar, both are same, 0.1 normal KCl. Since I have taken the principal electrolyte as KCl, the indicator electrolyte should have the same ion, because I have taken KCl, that is K plus using KCl. So, the indicator electrolyte, the anion should be a chloride ion containing. So, here they have taken cadmium chloride. So, the indicator electrolyte is cadmium chloride. So, potassium chloride, cadmium chloride. So, the anions are common. Now, what should be the condition for the cation? Now, here you cannot take potassium, this is an indicator electrolyte, we have taken cadmium. Here the principal electrolyte K plus has got the K plus ions that will be moving when an electric current is applied. And this cation of the indicator electrolyte will also be moving in the same direction as that of K plus ions. Now, what happens is they will be going to the cathode, both of them moving to cathode, both K plus as well as the cadmium 2 plus ions, both will be moving towards the cathode, and in this experiment the cathode is shown at the top. Now, when potassium moves towards the cathode, cadmium ions should follow potassium ions. It should not go before potassium ions to the cathode. So, it should be following the K, or you can say that the mobility of cadmium ions should be lower than that of potassium ions. So, this is a condition for an indicator electrolyte. It should have an anion in common, and the cation should only follow the cation of the principal electrolyte. Now, the movement should be in such a way that there will be a sharp boundary between the two electrolytes. Okay. So, you should take two electrolytes in this tube. One is potassium chloride, that is 0.1 normal, and cadmium chloride also of the same concentration, 0.1 normal. So, you are taking two electrolytes. Now, in this we have two electrodes, there is a platinum electrodes, both cathode and anode is platinum electrodes. One is given a negative sign and the other one is positive sign, and the positive ions they move towards the negative electrode. This is known as a cathode. This is a cathode and this will be the anode. Okay. Now, before passing the current, when we add the indicator electrolyte above which we place the potassium chloride, and you can see that there will be a sharp boundary. Now, when current is applied, as potassium ions move up and cadmium ions follow it, the boundary moves up. Let it move up to this position. Okay. So, the boundary moves up and this movement of the boundary is proportional to velocity or mobility of the K plus ions, right, because K plus ions are moving and the cadmium ions are following, and this movement shows us the speed of the K plus ions that moves under the applied potential. Okay. So, let this be the distance travelled be x. Let the time be t seconds. Okay. Now, the potential applied is E volts potential gradient. Is E. Now, mobility of K plus ion is equal to speed of K plus ion divided by potential gradient. Speed of K plus ion, potential gradient is E, that is we have already written, and speed of K plus ion means for t seconds it moves a distance of x. So, x by t will give you the speed of the ion, x by t divided by potential gradient. On rearranging we get x divided by E into t. So, t comes to the denominator. So, by measuring x, t and E, you can find out the mobility of K plus ion. In such a manner, you can determine the mobility of an ion using this method. Next, what we are going to see is the Kohlrausch's law. Kohlrausch's law states that at infinite dilution, the condition is infinite dilution, there is no other condition other than infinite dilution, when the dissociation of the electrolyte is complete, that is when lambda 0 m or lambda 0 EQ, whatever it is. Each ion makes a definite contribution towards the total molar conductance of the electrolyte, irrespective of the nature of the other ion with which it is associated. The condition is at infinite dilution. So, it is very important. Now, at infinite dilution, actually Kohlrausch's law is based on an experiment saying that suppose he has taken KCl and NaCl. Then he took another salt, let it be potassium nitrate and sodium nitrate. Okay. If the lambda m values are subtracted, that is here lambda m values lambda 0 m of these two values are subtracted, and similarly lambda 0 m values of these two are subtracted. Actually, in this case chloride ion, all these get cancelled because each one will be there. Now, the difference will be difference in molar conductance between potassium and sodium, and it was found to be 21.1. Again, in this case also, when these lambda 0 values are subtracted, both NO3 values will get cancelled because in both cases we have one each, and the difference between these two will be again 21.1. That means the difference in conductance between sodium and potassium is a constant at infinite dilution. It does not alter whether it is a chloride or nitrate or sulphate, whatever be the anion with which it is associated. Now, from this Coriolis law was formulated, because these experiments led to the formation of Coriolis law. At infinite dilution, when dissociation of an electrolyte is complete, each ion makes a definite contribution, towards molar conductance of the electrolyte, irrespective of the nature of the co-ion with which it is associated. Okay, that can be expressed as lambda 0 m will be equal to x moles of lambda plus m plus y moles of lambda minus m. This is for cation and this is for anion. So, cation as well as anions, like how many moles it is formed. Depending on that, if you add up that value, you will get lambda 0 m. So, for each ion, you can give a lambda 0 value for each, and that will be a constant. For example, if I take barium chloride, okay, what are the ions formed from this? You will have Ba2 plus 2Cl minus. If I take 1 mole of barium chloride, I will get 1 mole of barium ions and 2 moles of chloride ions. So, in this case, lambda 0 of barium chloride will be equal to lambda plus of Ba2 plus, that is you are having 1 mole. But in the case here, we have 2 moles of chlorine. So, it will be twice lambda minus of chloride ions. Okay. The ionic conductance all being measured at infinite dilutions. So, we are considering only at infinite dilutions. So, here that is what they have shown as x into, that is we are having cations, if we are having x moles, it has to be multiplied by x plus y moles multiplied by the ionic conductance of the anion. Okay. Now, let us see how will you write the expression in terms of Coriolis law for sodium chloride. Sodium chloride, as we all know, dissociates as Na plus Cl minus, each 1 mole. So, that will be equal to. Now, one more point to be noted is, that is capital lambda is used for the electrolyte, and for ions we use small letter lambda. Okay. And with a superscript plus for to show that it is a cation and minus for an anion. Okay. So, here we are having only 1 mole of sodium ions. So, Na plus lambda minus of Cl minus. Okay. Now, next let us see what happens if I am going to write down for lambda 0 of aluminum. In the case of aluminum, you have to just check its dissociation, slightly different, Al2SO4 thrice. So, this will be ionizing as 2Al3 plus 3SO4 2 minus. Here we will be having 3 sulphate ions and 2 aluminum ions. So, in this case lambda 0 m for Al2SO4 thrice will be equal to, you are having 2 moles of aluminum. So, 2 into lambda plus of Al3 plus 3 sulphate ions. So, 3 into lambda minus of sulphate ions. Hope you got it. So, this is how you have to write down for an electrolyte according to Coriolis law. Next, let us see what is the relation between ionic conductance and ionic mobility. Okay. They are related by the reaction. Ionic mobility is equal to ionic conductance divided by 96,500, and 96,500 is, we call it as 1 Faraday, that is 96,500 coulombs, and dividing it by 96,500 coulombs you get ionic mobility. All ionic mobility as well as ionic conductances are taken at infinite dilutions. It's to be remembered, we only consider these values at infinite dilutions. Okay. Now, let us see what is the ionic conductances with alkali metals. We know that alkali metals, lithium is the smallest one, lithium, sodium, potassium, rubidium and cesium as we come down the periodic table. So, this is the first group alkali metals. Now, we know that the mobility of the ions, they are faster moving when the ionic size is small. As the size of the ion increases, they find it difficult to move well through the solution, and therefore, their ionic mobility will be decreased. But, so in this case, since lithium is the smallest one, the smallest size, and therefore, lithium ion will be very small. If I take lithium, we are considering the ions, lithium ion, sodium ion, potassium ion, rubidium ion and cesium ions. All these charges are equal, but when compared with the sizes, lithium has got the smallest size and cesium has got the largest size. Now, these ions, when they come into solutions, what happens is, all these ions, they get hydrated. Okay. Once they get hydrated, the size of the ions increases. Now, the extent of hydration depends upon what? That is the charge density. Charge density for lithium is very high. Why? Because it has got a very small size, and therefore, this positive charge is spread in a very small area. When we come to cesium, it has got a very large size with a unit positive charge spread through the whole surface, such a big area. And therefore, charge density for lithium will be very high, and therefore, lithium attracts more water molecules. Usually, the solvent considered is water, more water molecules, and it gets very much hydrated, or you can say maximum hydrated. Why is that so? Because the charge density of lithium is very high, and therefore, the size of the lithium ion increases. Now, what happens? Hydrated ions, that is what it remains in a solution of electrolyte. Ionic sizes will be, lithium has got the highest, biggest size, greater than sodium, greater than potassium, greater than rubidium, greater than cesium. Now, the case is different. Here, lithium has got the hydrated ion, has got a larger size, and therefore, lithium moves very slowly, and therefore, when we compare the ionic conductances, who will be having the greatest one? That which has got the smallest size. So, hydrated ions, cesium has got the smallest size, and therefore, here the ionic conductance in the case of alkali metal increases in this direction. Okay. So, what is the reason for that? Lithium being small, it is mostly hydrated, and therefore, the hydrated ion size for lithium is larger, and therefore, lithium ions move slowly. While cesium being larger in size, it has got low charge density and less hydrated, and therefore, cesium moves faster than lithium. Next is abnormal mobility and conductances of hydrogen and hydroxyl ions, which is also known as Groth's conduction. We know that hydrogen atom and hydroxyl ions, they are hydrogen ions and hydroxyl ions. Both are very small ions, and they will be highly hydrated, and they will not move very fast. But in spite all these, both H plus and OH minus ions, they move very fast as if they were being carrying a large quantity of current. Now, what is the reason for that? And that is due to a special mechanism known as Groth's conduction, because we have an additional way to transfer H plus and OH minus ions. So, here you can see that is water molecule which has abstracted a proton contains a positive charge, and this positive charge is passed along towards the third molecule. And suppose if it is a current applied, this is the positive pole and this is the negative pole. In that case, you can see that here this is a bold line showing a actual covalent bond, and this is a dotted line showing a hydrogen bond. Now, what happens in this mechanism is just shifting of hydrogen bonds, that is, this bond becomes hydrogen bond and this becomes a normal covalent bond. By that way, the positive charge will be shifted to the next water molecule. So, here you can see that this is a hydrogen bond, this becomes a normal covalent bond, and at that time the positive charge will be on this water molecule, that is the second one. From this again there is a shift of hydrogen bond, that is, this bond becomes a hydrogen bond, this becomes already a normal bond. So, this is two hydrogen atoms attached to water molecule, and here this hydrogen being shifting to this water molecule, therefore, it goes as a proton, the positive charge changes to the third water molecule. In addition to movement of H plus and OH minus ions, we have an additional movement known as Groth's conduction, and thereby H plus ions carry more current than expected amount of current. In a similar way, hydroxyl ions also do the same procedure. So, here we can see that this is an OH minus ion. It contains a negative sign, and this negative sign is being transferred to this direction. See, it abstracts a hydrogen or a proton, you can see this direction. So, we have here we will be having a bond, and as a result this becomes again a negatively charged OH minus ion. I will repeat, that is, here this oxygen atom abstracts this hydrogen towards itself. What happens is the charge is lost while this OH will be carrying a negative charge. Again, this OH minus ion abstracts the next hydrogen atom which is hydrogen bonded to it, so that the negative charge is transferred to the next water molecule. And from this again it abstracts another hydrogen atom, and here the negative sign finally reaches on this water molecule. So, there is a transference of negative sign from this point, that is the first OH minus ion to the third one. Okay. And because you are having an electric field here, that will be positively charged, and here it will be negatively charged, and the shift of hydrogen bonds take place, and finally you have the negative charge shifted towards the right hand end. So, in this class we have been seeing what is ionic mobility, determination of ionic mobility in experimental method, Kohlrausch's law, that is by adding the ionic conductance of the electrolytes, then relationship between ionic conductance and ionic mobility, and abnormal mobility and conductances of hydrogen and hydroxyl ions. Thank you.